Hello everyone, my name is Brandon Pardi. I'm demoing our software pyQCM-BraTaDio today that I have developed under the guidance of Roberto Andresen Eguiluz for the team. And this software is designed to analyze experimental data from Quartz Crystal Microbalance Dissipation, or QCM-D, and it does a lot of basic visual analysis and also some basic modeling features, a lot of which are done typically in Excel manually and are just very time consuming. And this pipeline is designed to exponentially increase the speed at which people can analyze that data so they don't have to manipulate everything in Excel all the time. So before we get started with the actual tutorial, let's do a quick QCM-D background. We use QCM-D to quantify the absorption of protein to surfaces. We have a piezoelectric sensor which is excited to its resonant frequency via an applied alternating voltage. As you can see here in this diagram, we have the sensor, and this top line is its resonance, and then as we apply or add a film onto the sensor, this change here that we see allows us to see the amount of the mass coupled to the sensor. And these experiments are pretty large. They record a lot of data points over the course of typically several hours. Very time consuming to analyze these manually in a spreadsheet software like Excel, especially if you have a slower computer where this much data would run pretty slowly. And existing software that does what our software does is often proprietary, or it is unnecessarily complex, and we aim to provide a quick and efficient solution to rapidly analyze data. So to first get started, before you run any actual code to analyze the data, you're going to make sure you have all the packages installed, which is this file here. I know most people in the experimental field use Spider. All you need to do is just open this file in Spider, and then you'll hit the Run button up at the top. I'm using VS Code, so it looks a little different, but it's the same idea. You can also avoid any code editor and just use a terminal. All you have to do is navigate to the directory where you have downloaded the code, and then you can type python main.py to run the actual script. But like I said, we need to install the packages first, so we're going to do python install packages.py. And obviously I'm going to have all of these already installed, but this might take a minute for you as it installs everything and gets all the dependencies in order. Once you have that installed, we can go ahead and python main.py. And again, if you're in Spider, all you have to do is open the file, hit the play button, and it runs the same. You don't need to run any of these other scripts really at all ever, as main calls what it needs from each of these when it needs it. So upon running main, you'll see the user interface that you'll be interacting with. You have the four main columns, all the file information, selection of raw and shifted overtones, or the absolute values and the deltas, and then you have some options for what plots you want to generate. So the first thing you're going to do is select the data file. I'm going to show the first file we're interacting with. It is a QCMI experiment ESA. What the file looks like. There's a lot of columns, and you'll see the result after the file formatting that we don't actually use most of these. Go ahead and close that for now. Select the data file, this one right here. Again, this is a QCMI experiment, so the next step is to select where it came from. These are the 4 types we support. There will be instructions in the supplemental information of the corresponding paper for the software that dictate how you can use different kinds of file formats that are outside of these 4 natively supported ones. There's a manual way and a way you can adjust the code, but for now we're just going to stick to showing you the support. Next up is entering the baseline time. That is the time before the actual experiment begins, when you have a nice solid baseline. We use this for the shifted data section. We take an average of all the values in that range, and we subtract everything by that amount. So we have all of our values down at 0, 0. Next up is theoretical or offset. This is used for stuff in the modeling functionality. QCMI is nice because we are able to just grab the offsets from the data file. Same for OpenQCM. So if you select offset, note here reminds you of that. You don't need to actually enter any calibration or offset values, which we'll get into if you have something like QSense or AW sensors. And we can go ahead and submit file information. What it's going to do, it's going to take that file I just showed you and convert it to a standard format that pyQCM-BraTaDio reads. See here, this is what the file looks like after formatting. The values will be the same for the columns that we actually picked from. You can see here, this one matches this one exactly. Grabbed the channel A fundamental frequency, and we just converted it to a different name, and these names will be the same going forward. All the names of columns that we will reference, and we dropped a lot of columns that aren't necessary, like Gmax or GOFs, and we're only taking the frequency, dissipation values of each overtone that is available in the data file, as well as time and temperature. Okay, after you've entered the information for your data file and you've submitted it, everything gets converted. We can briefly talk about the plot options that are available to software. Change things like the font, label size, title font size, value font size, select all the little different font sizes of the plot itself. You can choose the tick direction, in, out, or both, where it's kind of in between. Change the scale of the time on the x-axis, which the default is seconds. Points to plot index allows you to limit the number of data points you actually use on the plot. There are some experiments that we've come across that are very dense as far as the amount of points they record, and especially on the multi-axis plot, which is this option right here, it looks messy and hard to see, so you have the option to plot every xth point. And then you also are able to adjust the bounds of data you want to plot if you only want to have the basic visualizations show a portion of your data. I'm going to leave everything as default for now, but once you have inputted everything you want, you will hit confirm selections. There's also a default values button, and there's also the colors you can change, where you just click on the button and you have this whole color hue map thing, or any of the basic colors here. You can also just do custom RGB values if you'd like as well. And then again, just confirm selections, and you can close this window. And anything that once you've hit confirm and close, you don't need to touch that. Once you open this again, you can close the software, you can close your computer, do whatever you want, come back to it. Those options are saved in a JSON file here. So whenever the software is open again, it remembers your options for the plots. Okay, so we have our file information, we have our plot customized. Now let's talk about the middle two columns. These are selections of the columns you want to plot. So you can select all of them. Do keep in mind some devices don't go up to the 13th or 11th overtone. So just keep in mind that your selections here match the available columns in the plot. If you don't, there is some error checking in this software that I will get to later, but it will let you know there is an error and that you will have to correct it. So we're going to plot all the raw data, we're going to plot all the shifted data. We're just going to go kind of crazy. Let's also do the interactive plot. It'll bring up a window that we can make selections in and view data and analyze everything further. It's also pretty essential for anything in the modeling section. So to use interactive plot appropriately, you'll have to select an overtone to visualize. Typically, we do the 3rd or the 5th because it's the cleanest looking. Do know that any operations that will be described later that are done in the interactive plot are done to all the overtones. It's not that this overtone is the only one that those operations get applied to. This is just the only one that we're looking at, so it's not too messy and we can see things better. This section here is the range being selected. So like I said, we're going to be selecting ranges in the plot, and the data within those ranges will have operations done and the data itself will get saved. And to remember for yourself, you can choose any kind of identifier you want. It can be numbers, it can be letters, it doesn't matter. Just something that you can, it's for you to remember. So for now, we're just going to do test and make sure to hit confirm range. And before we go into these options, let's just stick with the interactive plot. Make sure you enable it once you've selected if you want to do the interactive plot for shifted or raw data, and then you can submit. See here in the terminal, it's printing some things, just some sanity checks to make sure everything's working properly. This is what the experiment looks like for, again, the 3rd overtone. And note the y-axis says the change in frequency with delta to help distinguish but that this is the shifted data that we're looking at the interactive plot for, not the raw data. So in the interactive plot, this is where we make our selections. You can select anywhere you'd like, really, does not matter, but for experimental purposes, you're typically going to be making selections towards the end, right before each little dip. So right here, the blue bar you'll notice is coupled down here. You can make your selections down here if you want, and it'll match up here. Does not matter. Note you cannot make any selections on the right side. The right side is just reviewing. What you're reviewing here is a zoomed in selection of thin plot of your selection of data right here. And then you can see up at the top, these numbers are grayed out because that's what it grabbed from your selection here. But let's say you want to enter a more generic value, so we can do 3000, 3300. Hit enter, and it makes the adjustment down here as well. So your options are to select here, or type a selection up here, and the same happens either way. With our selections made in the interactive plot, let's take a second to look at the data that we've aggregated so far. First things first, in the raw data directory, again, this is the default directory where you can keep your data. However, with the select data file button, you can browse for files anywhere on your computer. However, when the data is formatted after you hit this submit file information, it will get saved here and referenced later, where the word formatted is prepended to the original name of the data file. The next thing we have for the plots that we generated, we're going to see so far 4, because we opted to plot raw and shifted data. This is the dissipation, change dissipation, of all the overtones. We have the change of frequency of all the overtones, and then these are the raw dissipation and raw frequency values of all the overtones. That is what gets plotted by default whenever you select these and don't have any of these extra plot options selected. The next bit of important data we've collected is in the selected ranges folder. We have clean all stats dis for dissipation and RF for resonant frequency. So let's take a look at the frequency one. See here, we have overtone, the average tracer frequency, the standard deviation of the change of frequency, as well as the median. This here is the range name, which is what I specified earlier. This is what you type in here when you hit confirm range. You can see test, and here we have test. And then it also records the lower and upper bounds on the x-axis of your selection, as well as the file that this data came from. You can see here there are more entries than just test. We have QCM-I test and QCM-I. This is because when you make selections, it does not overwrite until you reuse the same range. So let's go ahead and close this, and I'm going to show this next part in my code editor because it live updates instead of having to open and close the file over and over again. So we're going to open these back up. You can see here we have test in the green column here. These are what the values are. It might not change very much, but you can see it will update. Values are different now, again, just because it happens so fast. And you can see here that these other two ranges did not change at all. And if I do test 2, range, make another selection, then we have a new set of rows for our selection. If I do it again, test 2 will update, but test, QCM-I test, and QCM-I stay the same, because again, these do not get removed. They only get updated when you make a selection updating the same range. However, when you're ready to start from scratch, typically if you have a new experiment you're doing, or you're just opening it up for the first time in a while and you didn't clear it from before, there's a button here to clear saved range data, and you're going to see that all this is going to vanish, and now it's empty. And then if we make our selection again, let's just go back to test. Now we have just one selection of data. We can go ahead and close the interactive plot for now. Let's check out some of the modeling functionality. Now we have the averages available, sour by mass, thin film and liquid. Thin film and air is a work in progress, but we're going to come back to that one another time. And crystal thickness. Okay, so we'll just run down the list. The average of the overtones. And all of these plots be in the QCM-D plots folder and in the modeling subfolder. Go ahead and clear all these out. These are old experiments. Run this. Now we have two files that generate. We have the average change in dissipation for range test, because that's what we entered earlier. And then we have change in frequency for range test. And this is just a summation of the average Y values for change in frequency and change in dissipation from our selection earlier. Now let's go ahead and check the Sauerbrei mass analysis. See here we have two more files. This is the mass for each overtone. And then this is a more novel feature where we take the very similar plot to earlier, the change in frequency averages against the overtone number, and the slope of that is correlated to the Sauerbrei mass. So we have a Sauerbrei mass that corresponds to the slope of this linear regression fit. And it's kind of hard to see from this data, but if we zoom in, even if we zoom in, it's pretty hard to tell, but there are error bars on the y-axis for a standard deviation of the averages of this selection. Okay, so next up is the thin film in liquid, measuring the shear dependent compliance. Get another linear regression fit, and this one is the bandwidth shift, delta gamma n, against the overtone times the change of frequency and delta f. And then the slope of this line corresponds to the shear dependent compliance of the thin film. And lastly, we have the crystal thickness model, which doesn't actually depend on the selection we made in the interactive plot earlier. It depends on the offset data, which, as mentioned earlier, for QCMI is collected automatically, and for QSense will require some manual input, which we'll get into soon. Now, let's go ahead and have a peek at it. A positive correlated linear fit with a very strong arch squared, and we get a thickness of 0.3368 millimeters for this data. So along with the plots that those modeling functions generate, you'll see we have some more files in the selected ranges folder that we were in earlier. All of the modeling functions record the outputs that are sent to the plots for more specific analysis if you need to see exactly what those numbers are. So for the crystal thickness, we have the overtone and then the offset value, as well as the fit for the offset values, so you can compare, and then the actual crystal thickness at each of those. We also have the Sauerbrei output file generated from the Sauerbrei modeling functions. See here we have the average change of frequency and the error for it, as well as a few other things. We also have the calculated mass sensitivity constant C, which of course will be the same for all of them, as that does not vary with the overtone. Of course, as usual, the name of the range that it came from and the data source. And lastly, of the ones that we generated, we have the thin film in liquid output file. It's going to record n times the change in frequency, bandwidth shift, and then the shift fit that corresponds to it. Okay, before we move on from this QCMI experiment, we have the options for plots in the fourth column to check out as well. We can do a multi-axis plot where we take the change in frequency and change dissipation on two y-axis together with the time on the x-axis. Also normalize delta f with its respective overtone. Important note about this: whenever you normalize, everything that gets sent to the interactive plot and then used in modeling features, anything that goes into modeling is unnormalized unless the model specifically requires it. So this will only apply to anything that shows up in this plots folder, not in the modeling folder. Go ahead and give that a shot. You can also check out the change in dissipation versus change in frequency and temperature versus time. Drift correction is a bit of an experimental feature, so we're going to go ahead and leave that out for now. Okay, we go ahead and hit submit. Again, we only made some checks here. You can also uncheck the interactive plot because we're not using that anymore. Didn't change anything else over here on the left side, just left that as is. We're just investigating some of the options for the plot. We hit submit, and then it generates some more files over here. We have the change in dissipation versus frequency. We have the dissipation from before, that hasn't changed. Now we have the multi-axis plot. This one is where I was mentioning it's a little hard to read. It gets kind of messy, so this is where the plot index gets really useful. We have the normalized change of frequency. You can see here now all the overtones are much closer together. Then again, the two raw files have not changed. And then lastly, the temperature versus time. So there are all the features of this software. Go ahead and change gears now to show a QSense file because there's some more subtle nuances that we have to discuss. Okay, so before we start with QSense, I would like to point out why there are some subtle nuances we have to address. So you can see here, this column is the fundamental frequency, and then this is a QSense file on the right here, and on the left is the QCM-I file we were just working with. See, this is the fundamental frequency column for QCM-I. There's quite the discrepancy between 4 million and a small little decimal number. That is because QSense only records the delta values, whereas QCM-I also records the deltas, but it more importantly records the absolute values. So that's where the subtle nuance comes in. There are some file conversion features that are done to QSense that are not done to QCM-I. And if we select the appropriate data file, is QSense BSA experiment, and then we switch to QSense with the radio button, we have some labels that pop up. And this is to remind you that when using QSense or AEW sensors, there are some offset values that are required for entry. We're going to go ahead and leave this timeline or the baseline time just how it is and make sure offset is still selected. You can use theoretical values, but we're going to go ahead and use offset. You have two options for how you would like to enter them. You click the enter values here, brings up a window where you can type all the values in manually. And note that if you hit confirm with nothing in there, or even if you have some in there and just one is missing, you'll get a warning that pops up that these entries that are missing will be converted to 0. So make sure that you do not miss any entries in here where you have data that needs to be analyzed. So aside from a window, your other option is to, as it mentions here, copy and paste the values directly into a file in the offset data folder. While you cannot miss, copy and paste offset values here. You need to make sure you have the offset values from the experiment that corresponds to this. I have them in this file right here. All the spreadsheets today. And then want to make sure that you do not alter these two columns as it relies on the index column. And then all the header columns as well, make sure to leave those as they are. You can just go ahead and select everything here, copy it, then paste it in this one, make sure we save it, close everything out, and now we can proceed. Now proceeding is the same as it has been for QCM-I. That's really the only thing we had to take care of. There are some extra things that the software does behind the scene for QSense that it doesn't do for QCM-I, but as far as what the user needs to worry about, that is the only thing. Go ahead and hit submit, do everything just the same as before, everything will look the same. Do note that plot files get overwritten, so all of the ones in here now are going to correspond to this QSense file we just generated, rather than the QCM-I one from before. This one has a bit of a messy fundamental frequency, very noisy, but you can see here everything is still just as it was before. You can also go back into the interactive plot for this file it generates, and we're going to make a second. We're going to do test QSense confirm. And let's go ahead and make a selection at the very end here. And you can see again, everything updated. We have another set of rows for this selection. And just for posterity, we can go ahead and run through all the modeling features again. See all their outputs in the terminal below. Hello? confirm range. And before we hit submit, to bring the interactive plot again to test the modeling features. Now that we've taken care of that subtle nuance for QSense, all we have to do is, now that we've taken care of the offset data with QSense, everything else will work the same. We don't need to worry about any other changes or discrepancies between the two. Everything has been converted to one format, so we don't need to worry about any other differences. Go ahead and hit submit. You note that everything that was in the plot options folder, not the modeling folder, but in the main folder, will get overwritten. So everything here you're going to see is just for the QSense experiment, not the QCMI one we analyzed previously. See, this has a pretty noisy fundamental frequency, but I did include it just for posterity's sake, but everything else here will behave the same. You can also adjust you can also experiment with the modeling functions as well on the sense file. However, since we have two different experiments, what we need to do is go ahead and clear the saved range data before we go ahead and make our selection again. Now we made the selection, we close the interactive plot, modeling, run through this all again. Perfect. And now you can see here the modeling functions don't get overwritten, but we're going to have test QSense here, and all the ones that don't say test QSense, just say test. Those are with the QCMI experiment earlier. One last thing I would like to mention, we do have some error checking, as I said before. To describe what that looks like, I'm going to make a potentially common error. I'm going to ask the software to plot raw data, but not tell it what overtones I want it to plot, and hit submit. And here it's going to tell you, warning, user indicated plot raw channels, did not indicate which. There are several other error catching features like that. You can see the software will not crash, it will not have any issues. Still does everything else as it's supposed to, but you're going to raw dissipation and raw frequency plots will be empty. So it's just to let you know that the software will likely still execute, but there probably will be something weird that you didn't expect, and just to correct for it. Thank you everyone for watching this demo tutorial of the pyQCM-BraTaDio software. I hope you find this tool useful. If you have any questions, you can reach out to us. We are always happy to help possible. Thank you.